In example 17.6, we are asked to define a quadratic function f whose inverse map is also a function. Then define the inverse function f inverse and graph f and f inverse on the same Cartesian coordinate plane. So it says here that we're trying to define a quadratic function. And the only real condition we have is that the inverse map is also a function. In other words, we are trying to create something that will have an inverse function. Every time we want to create an inverse function, we have to have a function that is one-to-one. So let's think about a real basic quadratic function. That would be f r to r given by f of x equals x squared. That's the basic squaring function. It's one of the very first parent functions we learned. It, at the time, was just called the squaring function, but since then we now have another name for it. We call it the quadratic function. This would be the simplest function that we have. And if I graph this over the largest possible domain, I would end up with our very familiar parabola shape. And I'll go ahead and do that now. We'll call that f. But the problem with this particular quadratic function is that it's not one-to-one. In fact, all the quadratic functions that we have dealt with have not been one-to-one. So this presents a problem. It's not going to be possible to create an inverse function using this. But we've gotten into a habit of writing down the domain as being the largest possible domain. It doesn't say that we have to use the largest possible domain. It says we have to guarantee that there is an inverse function. So the way that we fix that is not by changing the equation. Changing the equation is not going to change the parabola shape of a quadratic function. That's just the way it's shaped. That's the way it is. But we can change the domain to something that's a little bit more acceptable. So let's say f is only going to have a domain of 0 to infinity. So let's redefine it this way. And then that means that whole left side goes away and we're only dealing with the right half of the parabola. It's still the same equation, we just restricted the domain. And now it's a one-to-one function. So I'm going to cross out that first attempt. This is no good simply because we used the largest possible domain and we didn't need a domain that large. So now that we have this, we can go through the procedure of finding the inverse function equation. So we're going to say y equals x squared, and we will switch the x and the y. And then this will give us x equals y squared. Take the square root of both sides, and we will have the square root of x is equal to y. In other words, f inverse of x will be equal to the square root of x. So let's plot that one. That's another one of our parent functions. We'll have the point 0, 0, 1, 1, and 4, 2. Call that f inverse. And our usual observation here about the line y equals x holds. And we can now define f inverse with a domain of 0 to infinity, mapping to r, given by f inverse of x is equal to the square root of x. So we were able to get the inverse defined and we have that original quadratic defined as well, and showed that the graph of f and f inverse passes the line of reflection symmetry there.